Hello guys, this is Abhijit and today I'll give a brief review of classical mechanics, mainly the Newtonian mechanics that you have studied during your plus 2. Okay, this won't be your BSc classical mechanics because it would include a lot of vectors and formalisms with subscripts like IJ, QJ and all of the things. So this is simple Newtonian mechanics. Okay, so let us start. So you might have studied about force. Okay, let me give you a short review of what force is. You see, in our world, the motion is a consequence of force. It means the moment you give force to an object, the object moves. Without force, there is no motion. Okay, so now what type of motion does the force create? The force creates an accelerated motion. So what is the meaning of accelerated motion? I've already discussed in our plus 2 notes. Still I'm telling. So when something is moving at say 5 meter per second square, okay, it means that at every 1 second the velocity of the object is increasing by 5 meter per second. Agreed? The velocity is increasing. So the accelerated motion means the velocity is increasing but with time. The velocity is increasing with time. So the acceleration due to gravity for Earth is 9.8 meter per second square. It means in each 1 second the velocity of a falling object increases by 9.8 meter per second. Okay, so force creates acceleration. Okay, you might be thinking now, what would have happened to a world where force would have created velocity? So let me write an equation on screen. So imagine a world where force is proportional to velocity. So what would have happened in that type of world? So if you can give a small thinking, a little bit of intuitive thinking, you can guess one thing. If we would have been living in a world where the force is proportional to velocity, it would have been impossible to throw objects. It would have been impossible to throw objects. Why? See, whenever we throw objects in our world, the moment we throw, we already gave it a final velocity. The moment it goes out of our hand, the stone goes out of my hand, it goes out with a constant velocity. And that constant velocity that the ball has got was given by my force that I used it to throw. Agreed? So in our world we can throw objects. So when I throw a ball, it goes to a certain distance. But in a world where force is directly proportional to velocity, it means that when there is force there is velocity. When there is no force there is no velocity. It means when you throw, it means when object move, it is due to force. Okay, so if something is moving at constant velocity, it is only due to it is only because the force is constantly acting. In our world we don't need this. In our world we don't need force to make an object move at constant velocity. Once we give it an acceleration, it will go on moving at constant velocity forever. But for this world where force is proportional to velocity, things will be different. Okay, things will be different. So you can also think, what would have happened to a world where force would be inversely proportional to acceleration? How about a world where force is inversely proportional to acceleration? Okay, give it a thought. These are fun, good stuff to think upon. Let us continue. Let us continue with our world. Okay, so as I explained, that force in our world creates acceleration. I hope this point is clear. Okay, so force is proportional to acceleration, and we already know that whenever two things are proportional, that means whenever we convert this proportionality into an equals to, there has to be a constant. Okay, there has to be a constant. This part I discussed in how physics equations are made. It's already been discussed. So can you guess what would be the constant that would replace the proportionality with an equals to in our case of force is proportional to acceleration? Okay, an intuitive guess will be mass. Now question is, why mass? Okay, because mass is the thing that is actually affecting the process force is proportional to acceleration. Now how mass is affecting the entire stuff? You see, whenever there is a big object, say the mass of that object is 20 kilo, and you apply 10 Newton force, it won't be moving with a very high velocity, you know, and it is difficult for that force to make it move at a very high velocity in short interval of time. Now imagine a very small object and you put 10 Newton of force, it goes faster, it will achieve very high velocity in small amount of time. Agreed? So mass is such a thing that is actually deciding what amount of force will create what amount of acceleration. So mass is the thing that decides what amount of force will create what type of acceleration. So I have a force and I have an acceleration. Okay, now a particular acceleration that will be created by a force will depend upon mass of the object. Okay, so force is equals to mass into acceleration. Agreed? Okay, so intuitively it has to be mass. So in this way you can sometimes guess the proportionality constant intuitively. Okay, most of the time the proportionality constants are the things that actually are coming somewhere in between cause and effect. For example, here the force is our cause and acceleration is our effect. Now a particular cause will create what type of effect is decided by mass in this case. Okay, I mean a particular force will create how much of acceleration will depend upon mass. So mass comes as a proportionality constant. I hope that this point is clear. Okay, so we have this formula, force is equals to mass into acceleration in our world. Okay, so continuing further, I have given a small problem. Okay, the problem says that consider a ball. Okay, consider a ball of mass 2 kilo and and a force of 10 Newton acts on the ball for 5 seconds, and a force of 10 Newton acts on the ball for the 5 seconds, and the question is what is the velocity of the ball after 5 seconds. Okay, it's very easy, you can calculate the acceleration. Okay, that has been done here. First we have calculated the acceleration. Okay, it's very easily done. Force by mass gives me the acceleration. Once you have the acceleration, you can calculate the velocity by the formula acceleration into time. Yeah, it's very easy. So the velocity that the ball attains after 5 seconds is 25 meter per second. Okay, 25 meter per second. Now can you tell me what is the velocity of the ball after 5 seconds? Okay, the question is what happens to the velocity of the ball after 5 seconds. Okay, see, here is a very interesting thing. The force acts only for 5 seconds. Okay, so the acceleration existed only for 5 seconds. So the maximum velocity that the ball has achieved is 25. Now once the time goes beyond 5 seconds, there is no force. So once the time goes beyond 5 seconds, there is no force. So if there is no force, there is no acceleration. So if there is no acceleration, there isn't going to be any change in velocity. So what will be the velocity after 5 seconds? After 5 seconds, it is going to be same. The maximum velocity that the ball has attained at 5 seconds, the velocity after 5 seconds is going to be same. Agreed? Let me give you another example. To explain you that this very important point. Okay, that acceleration exists till force exists. Once the force is gone, acceleration is gone. Okay, let me give you another example. Consider this is the ground. Say this is the ground or the surface of the earth. Now consider a ball of mass m. Okay, it falls down. Agreed? Consider a ball of mass m is falling. Now when the ball reaches here, the line that I have drawn, let me draw in another color. When the ball reaches the green part, suddenly I switch off the gravity. Imagine, you can imagine this stuff. Okay, so suddenly I switch off the gravity. So the moment I switch off the gravity, you know what happens? When the ball reaches the green position, say it has achieved a velocity v final. Now v final is the velocity that the ball has achieved at the green position. Okay, this final velocity that the ball has achieved at the green position was due to the acceleration that it was going through. Okay, now after the green position, I said that I am switching off the gravity. So the moment I switch off the gravity, there is no acceleration. Okay, so from the green part till the bottom, I mean till the surface of the earth, the ball will fall with a velocity vf. It's not going to increase in velocity, because the moment the ball reaches the green part, I switched off the gravitational force. So the moment I switch off the gravitational force, there isn't going to be any acceleration too. Okay, so what I want to depict here, a very important point, that acceleration exists till force exists. Okay, once the force is gone, acceleration is also gone. Now, so we understood that. Continuing, so the question, so the another part of the question says that what is the distance covered in 5 seconds? Very easy. You can put s is equals to half at square. This is a +2 stuff, and you can easily get the displacement in 5 seconds. Okay, so see, the above example that I have given you, okay, though it's very easy, but it conveys very important thing. One is the force that I have described above is a contact force. Okay, is a contact force. Somebody is pushing the ball. Somebody is pushing the ball. We also can have changing force. Okay, so imagine I have a ball. Okay, imagine I have a ball, and I put a force. Okay, and let that force be a function of time. So let this force be a function of time. So what would happen? See, if the force is a function of time, what would happen? The acceleration is not going to be same. Okay, so the acceleration will also be a function of the time. It means if a ball is acted upon by a changing force, then the acceleration is also going to be changing. The acceleration is not going to be same. So on earth we nearly experience a constant acceleration because the force is not changing near the surface of the earth. We assume the force is mg, so there is no change in m and there is no change in g. Okay, so let me give you an example of changing force. One type of force is the force that is generated when a ball moves through a liquid. Okay, so for example, consider this is a vessel. Consider this is water. Okay, consider this is water floating in air. Yeah, you can imagine all type of weird stuff. So consider this is water floating in air, and say this is a ball. Okay, initially moving through air, and the moment it enters the water, okay, it experiences a drag force that acts towards the left. So the ball is trying to move towards the right, but the drag force moves towards the left. And amazingly, it was found that the drag force is a force that actually depends upon the velocity of the ball. It actually depends upon the velocity of the ball. Okay, so there are forces like this also, and we can also have a force which is changing with velocity that I have discussed just now. So force that is changing with velocity. This type of force example are the drag force that I just explained to you. Okay, so let us continue further. Let us discuss about momentum. Okay, so why did we required a term like momentum? We are happy with the velocity, we are happy with acceleration, with time, with force, but what caused or what forced us to define something called as momentum? You all know that momentum is given as mass multiplied with velocity. Okay, so this is the formula, but why? The question is why momentum? Okay, now think about this thing. Consider you have a read the first sentence here. Consider you have a plastic ball, okay, and you have a moving train. The plastic ball is coming towards you at a velocity of say 100 meter per second, and the train is moving towards at a velocity say half of it, the 50 meter per second. Well, when both of the thing is gonna hit you, okay, so who's gonna hurt you more? Who's gonna hurt you more? The intuitive answer will be train is going to hurt you more. Okay, you might have seen those videos where a train is coming and there is a car stuck on the rail line, and the train seems to be moving slow. Okay, but when it hits the car goes away long distance. Okay, those type of collision videos are available on YouTube, you can see. So it's an amazing thing. So the train seems slow, but say it is moving at a particular velocity, but when it hits the car, it creates a lot of motion in the car. The car flies away and falls in a long distance. Okay, so here in the example, a plastic ball coming towards you at 100 meter per second and a train is coming towards you at 50 meter per second. The train is going to collide. When the train collides with you, okay, you are going to fly a longer distance and fall. But when the plastic ball hits you, all you have is a chest pain. Okay, not more than that. So something problematic here. Okay, the problem is you cannot use just the velocity to tell something about the motion of an object, or in other words, I cannot just use the velocity to explain the amount of motion that an object has, the amount of motion that a moving object has. Okay, so what else is important here? What is the difference between train and a plastic ball? The only difference is that train is heavier. So somehow a moving object, okay, contains what type of motion? So a moving object contains what amount of motion is determined not only by velocity but also by its mass, and hence to explain the amount of motion that a moving object has, we define the term momentum, which is a multiplication of mass and velocity, because mass is also an important thing and velocity is also important, so you just multiply them both. So this is how we came across the term momentum. Okay, an interesting thing about momentum is the rate of change of momentum is actually force. It is found that rate of change of momentum is actually force. It is true mathematically, it is true intuitively. Okay, why it is true mathematically? Okay, let me write why it is true mathematically. So we know that momentum is equals to, okay, mass into velocity. So if I differentiate the momentum, okay, with respect to t, so I actually get m, since it is constant will come out, I actually will be having dv by dt. Okay, so this dv by dt is nothing but its acceleration. So I actually get what? Mass into acceleration. So rate of change of momentum with time actually gives me force. Okay, rate of change of momentum with time actually gives me force. So it's clear. So momentum is clear. Now we move on to work done. Okay, so this is very interesting stuff. This is very interesting stuff. Why the definition work done is force into displacement? In a better way, I should say force dot displacement. Okay, so what is the use of work done? Why work done makes our life simpler? Okay, there is a beautiful reason behind this. You see, as I've already told you in +2 notes, that scalar quantities, they add just like numbers. Okay, so if you have an object of mass 1 kg and if you have object of mass 2 kg, and if you add them, you get 3 kg. Okay, you don't have to do anything, no big mathematics, just you add them like numbers. But vectors are some different quantities. You cannot add vectors just like numbers. There is a particular vector addition rule, okay, that decides how vectors add, and the vector addition rule actually comes from what? It comes from geometry. Please remember that the vector addition rule is nothing but geometry. and in geometry the direction of the lines are very important to decide what type of addition rule the vector lines are going to follow. Okay, so force, acceleration, velocity, displacement, these are all vector quantities. Okay, dealing with them is really difficult because the way they add, it's very not, it's not so easy. Okay, they follow some vector addition rule and it is so complicated. It says like if you have two forces at an angle theta, then the addition is root over of f1 square plus f2 square plus 2 f1 f2 cos theta. Okay, this is a big addition rule you have in front of you. But when you think of scalar quantities, all you have to do is just add them very easily. You just add them, you get one quantity, you get another quantity, and you add just like numbers and you get the total quantity. So what we did trickily is we defined very cleverly a scalar quantity. Okay, so how did we define the scalar quantity? We just did the dot product of two vector quantities, force and displacement. So what we have now, we have now a scalar quantity. Okay, so the same physics problem that you could have solved using vector quantities and you would have come across difficult addition rule will be simplified by this scalar quantity work done, and all you have to do is just add them, subtract them, and you get your answer. You see, you might have solved some problems in your +2. The same problem can be solved using force and acceleration, and the same problem can be solved using this kinetic energy and potential energy, which are part of work done. Okay, that I'll explain you now. You see, solving in terms of these energies and work done is very simple because you don't have to look for direction or anything. All you have to do is you look for energy. All you have to do is you look for energy. So making a scalar from two vector quantities makes our life easier. Okay, makes our life easier. That's why we define something called as a work done. Okay, to make our life easier, to make calculations easier. Okay, let's move forward. So it's written here that when you lift an object against gravity, the energy is stored as potential energy, and when you do work to make an object move, like you push an object, the moment you push an object you require force, and that pushing gets makes the object filled with kinetic energy. So the same work done, okay, when it lifts the object, the energy, there is something called as energy that is stored in the object. So if the work done is lifting the object, the energy stored, and they have given a particular name to that called as potential energy. And if you are pushing an object with a force F, okay, and you apply the force till a distance d or till a distance s. Okay, so what happens is when you apply the force till a distance s, all you do is you are making the object move. Okay, till s distance there is going to be an acceleration. After s there would be no acceleration. Okay, so this force that is acting on an object till a particular distance is actually giving a type of motion to the object, and that's why we say that the work done has created motion. Okay, we'll discuss the work energy theorem in details later on, but I am trying to give you some intuitive ideas. Okay, how we have first defined a scalar quantity called as work done from vector quantities to make our life simpler, and we saw how work done can give us terms. Okay, different terms, and we gave different names to different terms. Okay, let me give you an example. Look at this example. Okay, so there is a ball. Okay, here I have drawn a ball. Okay, there is a ball of mass m, and there is a force acting on the ball, and the distance the ball and the distance till which the force acted is s. Okay, so what is the work done? Work done is fs. Okay, now there is a very interesting thing. Okay, So what you do is you just write, let me make a derivation, let me make a small derivation to make you understand that why this is important. Okay, so let me write that first, that work done is equals to force into or dot displacement. Okay, now can you please tell me what is the work done? Who has done the work done? The work done is done by me. Who has given the force? The force was given by me. And who decided the distance? Till what distance I am going to give the force? It is decided by me alone. Okay, now what is force? Now force is equals to mass of the ball and acceleration that was generated in the ball. Agreed? The mass of the ball and the acceleration. Now when the ball has got some acceleration, so what is the distance it will cover? Yeah, you remember the formula, v square is equals to 2as. So s becomes v square by 2a, and that v is actually the final velocity. Okay, that v is fine. So I can write v square s as v square divided by 2a. This fetches me an answer of half mv square. So you see that initially everything was done by me. The work done was done by me, force was given by me, until what distance I will give the force, that was also decided by me. And in the end of the derivation, you get everything in terms of the ball. This mass is mass of the ball, and this velocity is the final velocity that the ball has achieved once the work is done. So can I say that something is moving from me to the ball? Okay, can I say that something is moving from the me to the ball? Because see, the entire derivation started with me, and the end of the derivation you get everything in terms of the ball. M is mass of the ball, v is velocity of the ball, the final velocity of the ball. Okay, so when I say final velocity, it means the velocity that the ball achieves here, this velocity, because the force acts till distance s, and till s there is an acceleration, and after s there is no acceleration. So here the ball will achieve a final velocity which is v. Okay, so the velocity that I have defined here in the derivation is actually this final velocity. The velocity that I have defined here in this derivation, okay, here in this derivation is actually this velocity, the velocity that the ball achieves in the end. Okay, so now you see the diagram I have drawn, that initially the ball is looking white, and as the work is being done in pushing the ball forward, it becomes green. So green symbolizes some kind of energy that the ball is achieving, and when the work is completely done till a distance s, I made the ball completely green, dark green. That says that the ball has achieved the maximum kinetic energy, which is equals to half mv square. Okay, and the position of kinetic energy by this ball when it hits when it hits you, you're gonna hurt. Okay, so you're going to get hurt. Similarly, when you lift an object up, so when you lift an object up, you do work. Okay, and that energy is stored as potential energy. So what I've done here is I have again made it green color to tell you that the height till which the object was lifted was h, and the total energy stored is mgh. Total energy stored is mgh. Now why did I say this is an energy? Because the object is still here. I understand, you would say that okay, we understand when something is moving it has energy, but how to understand that something is still, that is also in the air, how can we understand that it has energy? Well, the way to understand that it has energy is the moment you leave the ball, it's gonna fall. The moment you leave the ball, it's gonna fall, and when it falls, it's going to achieve more and more kinetic energy. So who is giving this kinetic energy? Actually the initially stored potential energy gets converted into kinetic energy while falling. Okay, so I can say that potential energy is just like a form of kinetic energy. It's a different form of kinetic energy, and they get converted into each other. Okay, from my point of view, there should not be two names, but there is two different names just to describe that the same energy can be stored in a still object and the same energy can be stored in a moving object. Okay, another example of potential energy is when you pull a arrow. Okay, when you pull an arrow in the bow, the potential energy is stored, and the moment you leave it, the entire potential energy gets converted into kinetic energy. Okay, so I hope you understood what I am trying to say in this portions. Okay, so this is work done. So very important thing, the work done is a scalar. The work done is a scalar. Even kinetic energy is also a scalar, and potential energy is also a scalar. Now question is, how is kinetic energy a scalar? Can you define mathematically that kinetic energy is a scalar? Yes, we can do so. You see the derivation of kinetic energy. Okay, the kinetic energy has half, which is a number and a scalar, no use. Mass is a scalar, nothing important, but the v square is a dot product of two vectors, which is v dot v. Okay, and we know that dot product of two vectors is always a scalar. Hence kinetic energy is also a scalar quantity. So hence kinetic energy is also a scalar quantity. So can you tell me how potential energy is a scalar quantity? Because displacement is a vector, g is a vector, so it is actually g dot h. Okay, so it becomes a scalar quantity. So everything is scalar here. The work done is scalar, kinetic energy is scalar, and potential energy is scalar. Okay, I hope I have given you some important intuitive answers to your questions regarding mechanics and why are you doing mechanics, sometimes in terms of force and sometimes in terms of energies. The same problem can be solved in two ways. Okay, so in further discussion we'll look at the rotational motion and the circular motion. Okay, and we'll look at how these terms like angular momentum and torque has come forward. Let me give you a short review about circular motion. You see, till now the force that we studied, all these forces, they caused straight line motion. Okay, for example, here I have studied a force, okay, F. You see, this force will only cause the body to move in a straight line. This force will only cause the body to move in a straight line, nothing more. But there are forces that can make the body move in circular motion. Okay, so the analogy of translational force, or the force that generates straight line motion, the analogous term to this force is torque. Torque actually generates circular motion. Similarly, when a straight line object contains momentum, that is mass into velocity, a circular object is also containing some momentum. Okay, that is the analogous of linear momentum is angular momentum. Similarly, when an object is moving in a straight line, it contains some energy, half mv square. Okay, similarly, when an object is moving in a circular motion, it contains energy called as rotational kinetic energy. But let me tell you one thing, that there is not a single bit of difference between linear energy and rotational energy. I'll prove in the next section that this rotational kinetic energy is nothing but can be derived from the linear kinetic energy. Okay, so we end our video lecture discussion here about the mechanics, and later on we'll go through more depths of things, and stay tuned for more lectures. Every week I'll be posting a lecture, so stay tuned for it. Okay, thank you guys for listening.